All right, guys and girls. So we were talking about the topic now of, let's do this in black, not red, of functional transforms, or operational transforms, I'm sorry. And one of the things that we found was that if I took the Laplace transform of a constant times a function, then this is the same thing as finding the Laplace transform and just taking that constant out. This is the multiplication of a constant. We also want to take a look now at addition and subtraction. So suppose we define h of t by definition as the sum of f of 1 and f of 2, and just for the heck of it, subtract f of 3, right? So what I'm doing is I'm making a new function by taking two other functions, adding them, and then subtracting. Further suppose that we know, or we are given, that the Laplace transform of f of 1 is known to be capital F of S. The Laplace transform of f of 2 is known to be f2 of S, and the Laplace transform of f of 3 is also known to be f3 of S, like so. Then I want to find, well, what is the Laplace transform of h of t in terms of things that were given, in terms of things that we know? Well, this is relatively simple to do. The reason being is if that happens to be h, well, then this is also the Laplace transform of f of 1 plus f of 2 plus f of 3 minus f of 3, like this. And I can then go back and revert to the definition, which means that this is the integral from 0 to infinity of e to the minus s times what we're taking the Laplace transform of, which is f of 1 plus f of 2 minus f of 3 times dt, right? Well, I can distribute that e to the minus st to all three of those functions, in which case I have e to the minus st f1 plus e to the minus st f2 minus e to the minus st f3, and I'm going to integrate with respect to dt again. Now, one of the properties of integrals is if you actually have the sum or the difference of various terms inside of an integral, one of the things that you can do is you can break them up into integrals individually. So this right here is the same thing as the integral from 0 to infinity of e to the st f1 of t dt plus the integral from 0 to infinity of e to the minus st of 2 dt, and then minus the integral from 0 to infinity of e to the minus st of 3 dt, like this. And we recognize each one of those separate terms as the actual Laplace transforms of each one of the functions individually. So this, by definition, is the Laplace transform of f1 plus the Laplace transform of f2 plus the Laplace transform of f3, or minus, I'm sorry, the minus sign is there. I don't need to carry it there. I'm not doing any sort of magic, like this. Notice that the big result, and this is the big conclusion, is that the Laplace transform, as you add and subtract functions like this, well, it's the same thing had you actually found the Laplace transform of each one of the parts, and then correspondingly in the Laplace domain, added and subtracted them together like this. Now, this is an extremely, extremely big deal. We had established in the previous video, right, that this was the case, right? We now established that this is true. That means that the Laplace transformation is a linear transformation, right? So putting some pieces together. So suppose that I had the Laplace transform of maybe some alpha 1 times f1 of t plus alpha 2 times f2 of t like this, and where alpha 1 and alpha 2 are constants, and this is the same thing as alpha 1, the Laplace transform of f1 plus alpha 2 times the Laplace transform of f2. My little brackets get worse the more I talk, so let me go back and fix that. This property of linearity is going to immensely, immensely simplify our lives, right? Tremendously. Because we can essentially, using tables, once again, of known Laplace transforms, we don't have to compute for given functions or any other functions the Laplace transforms over and over and over and over again. One of the things that we can do is we can kind of split things apart and use known results in order to find Laplace transforms, because again, it is a linear operation. And we'll see how this gets used in later videos.